Hello and welcome back to Multidimensional Integration, the video series where we talk a lot about how to deal with the Lebesgue measure and integral on Rn. And indeed, in today's part 16, we will define the so-called LP spaces and discuss a denseness result for them as well. However, as always, before we do that, I first want to thank all the nice people who support the channel on Steady, here on YouTube or via other means. And please don't forget, with a membership on Patreon or Steady, you can download a lot of additional material for the videos. For example, it's always helpful to look at the PDF versions for the videos. And now, without further ado, we can immediately start with the important definition of today. The definition is really similar to the definition of the integrable functions from the last video, but here we will fix a real number p. And this one should be just greater than 1 or equal to 1. And then for every such number p, we define a vector space of functions that we call curved LP. And then as always, the functions should be the domain given by Rn and the codomain given by the complex number c. And now you might already know that we want to consider integrable functions, but these in a specific way, namely if we take them to the power p, they should be integrable. Or more precisely, f in the absolute value to the power p should be in L1. This means we can just integrate with respect to the Lebesgue measure and have the power p inside the integral. And then the claim is just that this one is a finite number. And this is already the whole definition of LP, and you see the L1 case is also included here. Moreover, also similar to the case of L1, we get the so-called p norm with this integral. So every function in the space has a finite p norm, but you already know this is actually not a norm yet. This is simply because a norm should be positive definite, but the integral does not give us that. This is easy to see. If we have the 0 function and we change it at one point, the integral still stays 0. So this property is not satisfied, but you can also recall the other properties of a norm, and one of them is that a norm is always absolutely homogeneous. So we want to pull out scalars without changing the power of it, which means we have to take the pth root of the whole thing here. So this was not needed in the L1 case, obviously, but for any other power p, we have to add the root. In addition, I can also tell you that the triangle inequality for this norm is satisfied, but it requires some calculation. Hence, only the positive definite part is missing, and we can repair it by going to the equivalence classes of functions. So this is a standard thing to do, and what we get out is this new quotient space with respect to an equivalence relation tilde. And this one just tells us that two functions f and g should be equivalent if their difference in the p norm is equal to 0. In other words, the integral of f minus g to the power p should be equal to 0. And obviously this just means that they can only differ on a set with Lebesgue measure 0. This means they don't have to be exactly the same function, but almost everywhere they should coincide. And now we just put these functions into the same box, and then we calculate with the boxes. And the resulting vector space is what we call LP with a straight L, and this one has a well-defined LP norm. And in fact, this one is now an actual norm because we have fixed the missing part from before. So the result is that we have a well-defined normed vector space of functions. The only thing you should keep in mind that for every given function, there is a whole equivalence class that it represents. And now as a remark, I can also tell you that the space L2 is particularly interesting, because only for that value of p, the corresponding norm generates an inner product. And there it's not hard to see that the inner product of f with g should also be given by an integral. And there inside the integral, we have to multiply f of x with g of x. However, in the complex case, this is not enough. There we also have to add a complex conjugation, and usually I do that in the first component. So this is the L2 inner product, and you can immediately see the relation to the L2 norm. Namely, if you put the same function f into the first and the second argument of the inner product, you get the L2 norm squared. Or on the other hand, we can just add a square root to get the norm back. And here please don't forget, we also have to deal with the equivalence classes of functions to get a well-defined inner product. This is something you have to get used to because we will often calculate with explicit functions that represent a whole equivalence class here. And obviously there's no confusion at all if we consider continuous functions. Obviously, if we change a continuous function at any point, it's not a continuous function anymore. And in fact, the space we want to consider now is the following: the continuous functions with compact support in Rn. So any continuous function here lives completely inside a bounded set. And we have exactly the same result as for the L1 space, namely this space is already enough to approximate any integrable function. And this works even when the power p is involved as well. So more concretely, if we measure distances of functions with the LP norm, then this CC space is dense in LP. And as in the last video, we can make this statement really precise by choosing an epsilon. This means we can just take any small number epsilon greater than 0 and a p integrable function f. And for these two ingredients, we can always find a continuous function g that is close to f. And the closeness just means that f minus g measured with respect to the LP norm is less than epsilon. And you should recognize that this is exactly the same formulation as in the last video, but here we have formulated it for every power p. So you see, we have this nice denseness not only for L1, but for any LP. And actually, the proof of that is more or less the same as in the L1 case. Therefore, I think it's enough to tell you the crucial ideas again and what we have to change for the general p. The first thing you should note here is that we don't have to tackle a complex valued function because a non-negative function does already everything we want. Or in other words, every complex valued function can be decomposed into non-negative functions. And now the advantage of such a non-negative function is simply, as you might remember, that we can define a simple function that lies below it. This works by partitioning the y-axis, where we have the distance between two values given by 1 over 2 to the power m. And you also see that the last value we want to consider in the partition is given by m. So for every natural number, we get out a simple function that we call Sm. And indeed, by construction, the simple function lies pointwisely below our function f. Moreover, we also see that eventually the distance is less or equal 1 over 2 to the power m. Therefore, we definitely have the pointwise convergence of our sequence of simple functions to our chosen function f. However, we want to have even more. We want to have the convergence with respect to the p norm. And this one we can only get if we can apply Lebesgue's dominated convergence theorem. However, the standard formulation of the dominated convergence theorem is with respect to the L1 norm and not with respect to the LP norm as we want it. Therefore, we have to change the functions we consider a little bit, namely we want to have this difference in the absolute value to the power p. So let's simply call it hm and let's see if this one is an integrable function. And indeed, what we can use there is the fact that the pth power defines a convex function. This means there we consider a function with a real variable lambda. And if we send lambda to the power p, what we get is a convex function. And the property convex is quickly explained. You just have to look at the graph of this function. And because it's a power greater than 1, it looks like a parabola. Only in the case p is equal to 1, we would have the straight line. And exactly such a straight line we consider when we talk about a convex function. So convex simply means no matter which secant you put into the picture, the graph of the function lies always below it. More precisely, we have a greater or equal sign here, so equality is allowed. So to make it correct, you would say for any lambda here, you can take the value of the secant and the value of the function, and you have this inequality. Okay, so this is a convex function, and lambda to the power p satisfies it. And now the idea is simply to apply this fact to the middle point between 2 points. This means if we have a and b there, then the middle point would be a plus b divided by 2. And now the convex property tells us that if we put this into our function, then we are definitely not above the value of the secant. And the secant is just the middle point of the line, so we have a to the power p plus b to the power p divided by 2. So the result is that this nice inequality holds regardless which points a and b we choose. So finally you can see why this is useful, because we can apply it to our values of the two functions. The point is, what we have with hm of x is exactly the right hand side here. So we just have an estimate where 2 to the power p minus 1 comes in, and then on the one hand f of x to the power p, and on the other hand sm of x to the power p. And this is really helpful because by assumption f to the power p is integrable. And indeed we can simplify the whole thing because sm always lies below f. So we get a factor 2 which we can put to the front, and we have this nice inequality in the end. And this means we can finally use our dominated convergence theorem, because here on the right we have our integrable majorand. So please recall that we also have this inequality as well, which we can take to the power p, and then you see that we have the pointwise convergence of hm to 0. Therefore all the conditions of Lebesgue's dominated convergence theorem are satisfied. So the conclusion is that hm is integrable for every m, and it also converges in the L1 norm. And since the limit function is the 0 function, we have that the L1 norm of hm goes to 0 as well. And this is really nice because this L1 norm is exactly the integral we want to have. Namely just the difference of f with sm to the power p. So you see there's only the pth root missing to get the convergence with respect to the p norm. So in summary, we finally get the approximation with simple functions in the correct norm. And that's exactly the only change we needed here, because the approximation of the simple function with continuous functions works exactly like in the last video. The important part there was to apply the topological result that we know as Urysohn's lemma. So as a reminder, this one gives us the continuous function with compact support that we can call g. And now we can choose it in such a way that this distance here measured in the p norm is less than epsilon half. And then we just have to combine this with that part and the triangle inequality to get our result. So you see, we definitely want to use the standard properties of a norm. And this finishes the whole proof. We have the denseness result for LP as well. And as I have already told you, this one is really important and we will definitely use it in future videos. Therefore, I really hope we meet in the next video again, and have a nice day. Bye bye.